Okay, perfect. So we have a second application. After that physical insight we got into the active particle pressure, we want to have a look at the self-organization, which is completely driven by information flows, or the self-organization of particles by photon nudging. And you can see that as a kind of first example of how to create a swarm, but it's a very basic one. So if you really want to have a look at swarms, I recommend you to look in to the papers of Clemens Bechinger's group on the swarming and the forming of rotational phases, if you want. So this is about just two species maybe, or three species, which can sense each other. And if we take our fish, then this fish probably sees the other fish and likes it very much. So we would like to propel towards that. So it thinks about that, processing this information, and then decides with his fin to go into that direction. But the other fish may not like him very much. So he sees that fish and doesn't do the same kind of thing. He does something else and propels away from the other fish. You see, in that kind of way, each fish can have its own behavior, and they don't have to have naturally this kind of reciprocity in the interactions where you're bound to by the physical laws typically. And that makes all of these active processes, as I said in the introduction, very interesting, especially if they are based on signaling and information. There's no reciprocity anymore, like the action equals reaction principle in that. Okay, so let's have our fish here. Our fish are round and spherical and live in vacuum, of course. No, they live in a liquid, and we just want to decide on their distance, what we do with them. So if their distance is closer than any kind of set point REQ here, then they should propel away from each other. And if they are further apart than that kind of distance, they should propel towards each other. That's the simplest rule you can create, and you can map that even to some kind of idea how a force and a potential look, which don't exist, of course, but in principle, each of the particles is creating a repulsive force with a constant velocity. So the velocity is the force in the overdamped regime, as long as you have a distance smaller than REQ. And if once you are bigger than REQ with a distance, you have an attractive force or a negative velocity. And it turns into a potential which would have this kind of cusp shape. So it's just zero here in the middle. And then to the left, it will drive you to the right. And on the right, it will drive you to the left in principle. So that would be the idea of the force mapping and potential mapping we have. And the question is what we get out of such a situation. So I showed you that for a pair of particles, but of course we can have an arbitrary number of particles forming a kind of cluster. And the question is, how do you apply these pairwise rules now to a whole ensemble of particles? And that's very simple in terms of understanding, more complicated in terms of this equation. So you look how at the distance of these two particles, for example, and if they are too far apart, you propel them towards each other. And these two particles are propelled away from each other, maybe, because their distance is too close, and then you decide on that as well. So for this individual particle, you get therefore two directions of motion, one from that and one from that particle. So one could be just in that direction, the other one in that direction. So we sum up these unit vectors for this interaction directions, and then drive the particle in that direction with a constant speed. That's all. Yeah? So each particle has the same speed, and no matter how far you are, you always have the same speed. The only thing which changes is the direction. And that is mathematically expressed in that kind of rule here, or in that kind of equation, that the propulsion direction is nothing else than the sum of the individual propulsion directions with a sign corresponding to the distance of the particle from each other as compared to the set point. And then you just normalize that this is a unit vector and this goes in here, and this is our propulsion then. That's all we need. Yeah? Okay, so if you apply this kind of feedback rule to particles, you first of all do what I said. You get this self-organization of the particles, because they all want to stay from each other at that equilibrium distance, which is 7.2 micrometers here. Particles are 2 micrometers in diameter. So you get a dimer, and the bond length of that dimer is 2 micrometers. You get here, let's first do the trimer. All of the bond lengths are 7.2 micrometers. And then you get a tetramer, and then you have a problem because only these 4 bonds can have 7.2 micrometers, but not this one here, and also not this one necessarily. So in principle, this would be a structure which would like to be 3-dimensional. So this particle would sit on top of this plane here at 7.2 micrometers from all of them. And then you would fulfill our rule, but you can't because everything is 2-dimensional. So this is a kind of frustrated structure. And so do all the others are frustrated structures. So overall, they are at such a distance that there's also no hydrodynamic flow field anymore influencing them. There's only information which is in present, and that tells them to go into specific locations which we have not designed, which are just appearing or emerging. Yeah? So all of these structures exist only in non-equilibrium, and of course also are highly dynamic, as you will see in a second. And for all of the structures, you propel all the time all of the constituents with the same kind of speed. Yeah. So interesting enough is that here square-like shapes or non-hexagonal shapes also appear. And the reason is just that you have no cutoff in the interaction. So all particles attract all other particles with the same kind of strength, no matter how far they are apart. So the interesting thing starts now here also at that point when you look at the dynamics, and there you clearly see here an oscillation of all of those structures here. The dimer, the trimer, and also the tetramer shows this kind of bond length oscillations. And these structures are highly dynamic, and they can also diffuse around. So this dimer will eventually go into a certain direction. And here you've seen that we adjusted the position of the object, right? Okay, so if you analyze that a bit closer, you go to the center of mass frame of that object and look at the position of the individual swimmers in the center of mass frame. And there you see that they are doing that here in kind of circles. They're moving back and forth apparently, and they are rotating around somehow. So if you look at the density of the trajectory points in the radial direction, you can calculate actually a kind of effective virtual potential, a potential in which the particles effectively move. So if you remember what we did at the beginning, this is was like this cusp-shaped potential. But what you measure now as a virtual effective potential is more a box-like thing, because the particle is bouncing back and forth, and it looks like it does some undamped motion here in that kind of box potential, which it is, of course, not really doing. So the bond length itself will fluctuate around these 7.2 micrometers and have a strong oscillation. Sometimes it goes here to smaller distances and so on and so on. But you can analyze it a bit further, and that's what you would do in a so-called principal component analysis. I mean, you don't have to do that in that kind of principal component analysis, but you can. This is the easiest model-free way, and if you are interested in it, it's a really powerful technique. So essentially, that means that you dissect your particle fluctuations into directions in which the variance of the fluctuations is biggest. And all of these directions are orthogonal to each other as a new condition. So in principle, you have 2n minus 2 principal modes. For 2 particles, there are actually 2 principal modes which you can detect, and that are a stretch of the bond and a rotation of the whole object. So these vectors are the outcome of the principal component analysis. It directly gives you that from an analysis of the variances. And if you look at the dynamics of the individual components, for example, the stretch, you see here that it is almost triangular. You have that kind of triangular motion. Sometimes the amplitude is not that big, but it looks almost triangular. And this is one of the findings. And the other finding is that if you look at the autocorrelation of that triangular motion here, which is the zeros principal component here, you take that kind of principal component and you project the motion onto that onto these vectors here, then you get this oscillating autocorrelation function of the bond length, but which decays in amplitude approximately exponentially here in that case, right? A similar thing can be found for the second mode here, mode number 1 actually, which is the rotation of that. It also seems to oscillate, but with a much faster decay time than this one here. So what you see in summary from the experiment is that the bond length fluctuations are actually having a triangular shape. So the xtr is here nothing else than a triangular function which depends on time with a certain phase and a certain amplitude, right? And the autocorrelation is roughly an oscillating function as well. It's a cosine times 2 pi t over capital T, and t is the period of oscillation, and apparently the amplitude decays with another decay time t2 here in that case. So first of all, this is only an assumption, but if you look a bit closer at the Fourier spectrum of a triangular function, you will see that it contains the odd frequencies, a sum of odd frequencies here in that triangular function, where the lowest frequency is actually the one which is given here. And so this is a reasonable assumption that this is the only frequency which contributes here really to the autocorrelation decay. Okay. So why does it now oscillate, and what determines the frequency, and what determines actually the decay of this correlation function in a way? So there you have to look really at the feedback loop and what you're doing. And I'm just explaining that to you pictorially. At the end, it is kind of obvious again that it has to be like that. So we have a negative feedback loop in principle, which would do that with a finite time resolution. So imagine that you have taken an image of your particle. From that image, you take the location of that particle, and you also have the second partner in that kind of experiment where you would like to propel to or go away from. So you have two particle positions from which you can calculate the distance, which is the faint arrow here. So you would actually like to propel along those two directions. So you decide to set the laser positions here at the green spot and at this green spot, and this would help you to propel exactly in this kind of direction. But what you actually do is you take an image and calculate based on that image the location of your laser, and that takes some time. And the next time you apply that, you have the next frame already being recorded, and in the next frame, which is now our current frame because we apply the laser there, the particle's at a different position because it has diffused and it has been driven to a new position. So you have that kind of delay time in your interaction of the laser or response of the laser to your actual situation. And that leads to the fact that the particle is now at a new position, and the particles are propelled not in a direction in which they should go, but in a different one. So this is here, this kind of arrow and this kind of arrow, so they are really going sideways in a way, right? So this is creating actually any kind of, or all the dynamics in that system together with the diffusion. So you can write down, first of all, for that vector between the two particles, so the difference vector, Langevin equation, again, here it is, again, surprise, surprise, which is r dot 1, 2, this the distance vector, is 2 times the velocity at which they are propelling towards each other in the center of mass frame. It's 2 times the same velocity, plus diffusion term, and there's 4 times the diffusion coefficient because you have the relative motion. So the diffusion is twice as strong, and this is again your unit variance noise, which you apply here. So if you look at the velocity and apply our feedback rules, then it looks the following way, that the particles are propelled towards each other, also with a factor of 2, times the velocity of propulsion of each individual particle. And then the direction in which they are propelled is given by this sine function, which measures the difference between the bond length, which is currently existing or existed actually a time ago, minus the set point, and it goes into a direction which was also the direction a while ago. So both of them contain now exactly this kind of delay I talked about. So you respond a certain time delta t later, and at the time delta t, you have already a new position, and so on. And there's, of course, also the diffusive term here still. So overall, that means now for the bond length, not the vector, but the bond length, that it's roughly like this here, described by this, again, the signum function. And here it's now a distance, except then it's not anymore a vector, which I plotted here. So you see, this is a signum function, and that is actually that kind of rectangular step function we had before given as the force. And if you integrate that, of course, this rectangular function will give you a triangular function, and that triangular function will have an amplitude and a certain phase, which you can determine by putting that ansatz into that kind of Langevin equation finally, right? So overall, the dynamics of our particles is twofold. First of all, you have oscillations which occur due to that delayed interaction. The delay in the process of calculating the response to images is delayed. This delay is delayed, of course, yeah. And due to that, you get this dynamics. The amplitude is controlled by the swimmer's speed, of course, because here you have the swimmer's speed in front of that. So it should play a role. And there's additional Brownian motion. And if you think about what that Brownian motion does, is it creates from time to time a phase jump. So while the oscillation would be without any kind of noise coherent over all times, from time to time you have a phase jump, and that phase jump is causing a dephasing. And that's why I called that decay constant in the autocorrelation T2, because this is like a dephasing time. If you have some experience with spectroscopy or magnetic resonance, then you probably know what a dephasing time is. It's exactly like that here in this case. So overall, as a summary, that means for the dimer, the oscillations have a period, and it turns out that if you do that math, inserting the ansatz I presented to you into the equation, that your oscillation time period is actually 4 times the delay time. So there's nothing special about that. That comes readily out of this kind of equation, and this will be important for your exercise. The amplitude is controlled by the swimmer's speed, so they move with twice the speed towards each other. So the total amplitude will be twice as the velocity times dt, so 4 times the velocity times dt. And the dephasing is completely controlled by Brownian motion. You get an approximate expression that is given now by the amplitude of the motion squared divided by 2 times the diffusion coefficient. So the bigger the amplitude, the bigger is the dephasing time. So it takes longer for them to dephase. If you have small amplitude motion, of course, Brownian motion plays an important role, and your autocorrelation will dephase immediately. So that's all. I mean, that's all which in principle is going on in that very simple system. But it tells you that, for the dynamics of the feedback loop is important, and that's not only true for active particles which are made out of gold, that is true for any kind of feedback loop also in the real world, which is implemented in our fish, for example. So now you could go to more complicated structures, of course, and then also analyze that. And then starting from these more complicated systems, it becomes evident that the principal component analysis could be of important use. Here for a trimer, you have 2 times 3 particles minus 2 principal components. These are the 4 components you have. They have different amplitudes systematically. This is the size of the fluctuations here. And if you look at them, they perfectly match the normal modes of a triatomic molecule. So you have a symmetric stretch, a bending, an asymmetric stretch, and a rotational mode here, which is present in that molecule. And you can describe all that nicely. And you see how it also maps quite intuitively to something where you really have maybe harmonic bonds between the individual atoms in a real structure. But of course, this is only formed by information flows and the delay in the system. And that's now something which we can analyze a bit more and think about that. So if you know about fluctuation theorems, you probably have heard about that. You know that they describe relation between a path, or the probability for a path taken in a certain direction, and the path backwards in a time reverse direction, and related to some the energy dissipation which occurs during that process in the forward direction. So typically, if you have two elements like the red and the blue one here, and they create a state where they bind to each other, create a more organized state, so a state of lower entropy. To be stable in that state, you need in the forward direction a certain amount of energy to be dissipated that you can't go the way back symmetrically. Right? So this is what is stated by a fluctuation theorem like this here, for example, and it compares this kind of dissipated energy to the thermal energy which is available in the bath. So if this one is pretty large, then you can't provide enough thermal energy to make that reverse. Okay, so you can think of that now in the following way, that there must be something in our system which creates that lower entropy state of two bound particles. Of course, the normal state would be that they propel throughout the system to all kinds of places which are available and randomize their positions so that they are equally distributed. But by switching on that feedback control, they suddenly go to a state which is of lower entropy, where they're bound to each other. And that kind of entropy has to go somewhere, or that extraction of entropy has to come from somewhere. And it comes from our feedback apparatus. So our feedback apparatus itself produces entropy. It heats up the environment because we have a computer which is generating heat and all of these kind of systems. But it has a negative entropy flow, which is you suck out entropy due to that information from the environment. But there's also an additional amount of heat you supply, because you heat the particles here, and that heats up the environment and propels the particle. And that is what we call a kind of housekeeping heat. So that's always there. No matter if the particles are bound, they always propel with the same kind of speed. So you dissipate the same amount of energy due to the propulsion. But it is this kind of S minus dot here, the entropy production rate, that is negative, that keeps the order, and which is extracted by our feedback apparatus. But nevertheless, we can measure the PA, and we can also look at the probability to find a particle at a certain distance after we have watched it. So we take a snapshot, we take the distance of those particles and measure how far they go after until the next action is applied. And this is the rate of entropy that has to be extracted from the system to keep the structure stable. And it turns out that this kind of entropy is related to the propulsion absorbed power, so the power that is really going into the propulsion of the system, divided by the temperature multiplied by the efficiency of the propulsion mechanism we have. So overall, that tells you the structure you form is due to information you extract from the system, and you gain about the system. And the dynamics is, of course, based on the feedback loop and the bandwidth of that feedback loop. And that are also the key things you should remember, that also if any kind of assembly forms due to a signaling, then it's not because there's some kind of lowering of the free energy, which is based on physical interaction, so internal energy, but there's an extraction of energy, entropy involved by any kind of information processing. This is one of the things which is prominent in swarms, of course, but could also be applied to ensembles of cells and any other kind of systems where you have this kind of information flows. And the second thing is that the dynamics in these systems is largely determined by delays, activity, and Brownian motion. And that's also something where you will come back to in your exercise. And then the question is, of course, where you can go from here again. And there are lots of examples. I mean, the best examples are probably the work here on the criticality and also the quorum sensing, very similar. So you can also create a rotating state like this from other interactions where this experiment is here from. You can create swarms, and in these swarms you cannot only have a delayed action, but actually many higher organisms have a kind of inception or a kind of anticipation of where to go. Because if you catch a ball, you catch the ball not because you're particularly fast in your reaction, but your brain just estimates where the ball will arrive, and then you put your hands there. So you have an anticipation, you look into the future. And the same way, you can also create now mixed particle systems where all of the particles have different delays, and it creates really complex kind of dynamics overall and gives you new effects. So these are things to explore, and you might have also different ideas of what to do in general.